In this video, we look at the first of the three theorems from vector analysis, which is known as Green's theorem. So what we have to do is we consider a domain D whose boundary C is a simple closed curve. That is, it's a closed curve that does not intersect itself. We denote C, so we denote the boundary of a domain as partial D. The boundary orientation of partial D is the direction to traverse the boundary such that the region is always to the left. So what we do is we imagine ourselves walking around the domain. The positive orientation is the direction at which that boundary, so the entire domain, would be on our left. We shall assume that the components of all vector fields have continuous second-order partials, and that the boundary of D is smooth or piecewise smooth. Now, with all that preliminary, this is Green's theorem itself. Let D be a domain whose boundary is a simple closed curve oriented counterclockwise. Let F equal the vector of F1, F2 be a vector field with component functions that have continuous partial derivatives in an open region containing D. Then the circulation around the boundary of D of f dot dr is the double integral over D of partial of f2 partial x minus partial of f1 partial y dA. What this theorem is doing is it's allowing us to convert a circulation, a path integral, a closed path integral, into a double integral. To prove this theorem, we make a simplifying assumption. Specifically, we're making the assumption that the boundary of D can be described as the union of two graphs, y equals f of x and y equals g of x, with g of x less than or equal to f of x, and also as the union of the two graphs x equals h of y and x equals k of y, with k of y being less than or equal to h of y. Now, since f dot dr can be written as f1 dx plus f2 dy, we can construct two separate equations. The circulation around the boundary of D of f1 dx is equal to negative double integral across D of f1 partial y dA, and then also the circulation, this here should have been partial D. So the circulation around the boundary of D f2 dy is equal to the double integral over D of partial f2 partial x dA. Then the proof of Green's theorem comes down to proving that this equality holds, and then proving that this equality also holds. If we can prove both equalities hold, then we have proven Green's theorem. In this video, we're only going to prove this first equation. Right? So we're not going to prove that one. The proof of the second equation will be left as an exercise. So to prove this first equality, write the circulation along the boundary of D of f1 dx as the circulation across some curve C1 of f1 dx plus the circulation along some curve C2 of f1 dx, where we're going to define C1 as the graph of y equals g of x, and we'll define C2 as the graph of y equals f of x. These will be parameterized from left to right as follows. So C1 will be parameterized by R1, which is Tg of t, for a less than or equal to t less than or equal to b. And then C2 will be parameterized by R2, which is Tf of t. Again, a less than or equal to t less than or equal to b. However, using this, C of 2 will be oriented right to left, which is not the correct orientation. It needs to be, oh, I'm sorry, this is being oriented left to right, but we need it to be oriented right to left. So to do that, we just write that circulation is negative to flip the orientation. So we now write that the circulation along the boundary of D of F1 is the circulation along C1 of F1 minus the circulation along C2 of F1. This becomes, again, my apologies, this should have been boundary of D. This becomes the integral from A of F1 of T G of T dt minus the integral from A to B of F1 of T F of T dt. And this can be written as a single integral, which is shown right here. Right, remember, this is how we evaluate line integrals. By the fundamental theorem of calculus, F1 evaluate Tg of t minus F1 evaluate Tf of t is the integral from f of t to g of t of partial F1 partial y. And we can flip the limits by multiplying by a -1. So this is negative the integral from g of t to f of t of partial F1 partial y. Plugging this back in to up here, we can write that the circulation along the boundary of d of f1 dx is the integral of negative integral partial f1 partial y dy then dt. Well, this is an iterated integral, so it can be written in this form. But notice, t going from a to b, y going from g of t to f of t is our domain. So that is just negative the double integral along the domain partial f1 partial y dA. The equality is thus established, and that completes our proof of Green's theorem. Again, remember the second equality is being left as an exercise, but it is done in much the same way. Okay, now an example. We wish to verify Green's theorem for the circulation along a curve C of x, y squared, comma x, dotted with dr, where C is the unit circle that is being oriented counterclockwise. All right, so the unit circle, I'll just quickly draw that up here. All right, there's our unit circle, so this is the curve C. Well, by Green's theorem, what we have is the circulation along that curve of x, y squared, x dotted with dr must equal the double integral along the domain D of partial f2 partial x minus partial f1 partial y dA. Right, so the domain is this shaded region inside. So what we have to do is we evaluate both of these integrals and show that they evaluate to the exact same thing. Then the verification would be complete. Let's first look at the line integral. Now, we can parameterize C, r theta equals the radius, which is 1, times cosine of theta, then the radius times sine of theta. And since it's the circulation, it's over the entire unit circle, so theta will go from 0 to 2 pi. This will then lead us r prime of theta, negative sine theta cosine theta, so our circulation is equal to the integral from 0 to 2 pi of now the vector field evaluated at our parameterization cosine theta times sine squared theta, comma, cosine theta, now dotted with that r prime. d theta in this case. Doing out that dot product, 0 to 2 pi, we'll be left with negative cosine theta sine cubed theta plus cosine squared theta d theta. Integral from 0 to 2 pi. What we're going to do is we're going to break down this right here, this cosine squared theta, which will give us 1/2 plus a half cosine of 2 theta, and then minus that cosine theta sine cubed theta d theta. If we look at cosine of 2 theta, its period would be pi. But we're integrating from 0 to 2 pi, so we're integrating over 2 full periods. Well, that whole thing will wind up integrating out to 0. Same thing with the sine cubed theta. The sine of theta has a period of 2 pi, and we're integrating over one of its periods, so that will wind up evaluating out to 0. So really what we're left with then is the integral from 0 to 2 pi of d theta over 2. That's theta over 2, as theta goes from 0 to 2 pi, which is just pi. Now we need to look at the double integral. Our domain can be described 0 less than equal to r less than equal to 1, 0 less than equal to theta less than equal to 2 pi. Thus, the double integral over the domain of 1 minus 2xy dA becomes the integral from 0 to 2 pi, integral from 0 to 1 of 1 minus 2 cosine theta sine theta, 2r squared cosine theta sine theta dr d theta. Now if we look at d theta first, once again, we will see that whether we choose u to be cosine or u to be sine, we're still integrating over one of its periods. This whole thing will wind up going out to 0. What we are then left with is just this 1, dr d theta. Integrating with respect to theta, we get just 2 pi, integral from 0 to 1 of dr. My apologies, I forgot I need an r out here, so this is actually r dr. And this will give us pi r squared evaluated from r equals 0 to 1, which is just pi. As we can see, pi here, the line integral also gives pi. The verification is thus completed. Now, in this case, in my personal opinion, the double integral here was easier to do than the circulation. That may not necessarily always be the case, but if you find yourself having trouble parameterizing a boundary, and you know it's a closed boundary, then we can use Green's theorem to convert it to a double integral, and that may be easier to evaluate. What we're going to do for the rest of this video is look at some alternate forms of Green's theorem. First, we shall consider the circulation form. If we write the vector field f as the three-dimensional vector f1, f2, 0, then the curl of f becomes negative partial f2 partial z, partial f1 partial z, partial f2 partial x minus partial f1 partial y. However, f1 and f2 are strictly functions of x and y. So these two pieces would be 0. And this is what we'll be left with. We define a new operation, call it del z cross f, to be del cross f dotted with k hat. Right? Notice what that's going to do is it's going to give us 0, 0, and then whatever the k component happens to be. Using this new operation, we are able to write Green's theorem now in this form. And this is known as the circulation form of Green's theorem. The second form we look at is known as the flux form. For a simple closed curve C, we are interested in the flux across the curve in the direction out of the enclosed region, which we call the outward flux. Now recall that this is given by the circulation of f dot n ds, where n points away from the enclosed region. Now let C be the parameterization, or the curve parameterized by r of t equals x of t, y of t, for a less than equal to t less than equal to b, such that r prime is not the 0 vector. The unit tangent would be this here, and so the outward normal would be given by this. Then the flux of f out of C, right, will be the integral from a to b of f dot n times the norm of r prime. F dot n would be this here, then times the norm of r prime. So the norm of r primes are going to cancel out. We're going to be left with this. But y prime dt is just dy, and x prime dt is just dx. Now if we apply Green's theorem, this is what we find. And this is known as the flux form. Oh, I'm sorry, this is not the flux form, not yet. Because we want to look at this right here. So we're now going to examine this piece. Notice that's just the divergence of f. Using that, we can now write in the flux form, which is the circulation along the boundary of D of f dot n ds is the double integral along the domain of D of del dot f dA. And we're going to use this now to calculate the flux of this vector field out of the unit circle. Now flux, remember, we just saw, is given by this integral. It's the circulation along the boundary of D, f dot n ds. But by the flux form of Green's theorem, this is just the double integral along the domain D of the divergence of f dA. Now the divergence of this would be 3x squared plus 3y squared plus 1. Since we're dealing with the unit circle, we'll go from 0 to 2 pi, 0 to 1. Now convert the integrand into polar. 3r squared cosine squared of theta plus 3r squared times sine squared of theta plus 1, then times r dr d theta. This time I did not forget that extra r. This piece right here is just 3r squared. This becomes the integral from 0 to 2 pi, integral from 0 to 1 of now 3r cubed plus r dr d theta. Now we have no thetas. Integrating entirely with respect to theta allows us to pull out a 2 pi. We are thus left with 2 pi times 3r to the 4th over 4 plus r squared over 2. Evaluate from r equals 0 to 1. This will leave us with 2 pi times 3/4 plus a half, which is 5/4. Which leaves us with 5 pi over 2 as our outward flux. And that concludes our video on Green's theorem. The next video in the series, which will also be the last video in this series, will be the 2 remaining theorems from vector analysis, Stokes' theorem and divergence theorem.